Recent catastrophic events, such as the earthquakes in Nepal and Tohoku, Typhoon Haiyan, and several floods in Europe, have demonstrated that local civic administrations and emergency services have difficulty managing emergencies effectively. As a result of these catastrophes, the entire local society is thrown into chaos. In addition to the human lives lost, these crises have financial ramifications that are often difficult for afflicted countries to recover. The search for human survivors on the incident site is a priority for fire and rescue services in the event of major disasters. This is a difficult and risky job that all too frequently results in the deaths of human crisis managers. Unmanned search and rescue (SAR) devices could be a useful tool for saving human lives and expediting the search and rescue operation. Indeed, an increasing number of robotic equipment are leaving the controlled lab environment and being deployed and integrated into citizens' daily lives. Automated manufacturing plants, as well as the widespread use of consumer drones and the rise of autonomous vehicles in public spaces, are notable examples. These robotic gadgets could also be useful in search and rescue operations. Of course, this does not imply that robotic instruments will be easily integrated into search and rescue operations. On the contrary, the search and rescue environment is particularly tech-unfriendly, as solid solutions that can be deployed fast are essential. Indeed, one critical factor must not be overlooked: robotic equipment must not be designed with the goal of eliminating the necessity for human search and rescue personnel. Instead, these robotic assets must be viewed as yet another tool in the vast toolset of human search and rescue workers, allowing them to do their duties more effectively, quickly, and safely. Each of these statements is expanded upon in the following topics. First, advantage is better. As previously stated, robotic search and rescue tools exist to help human rescuers. One of their key advantages is that they can improve aid workers' situational awareness by providing a better and higher quality view of the nature of the crisis. Indeed, robotic technologies can provide more significant insights by viewing disaster scenes from a perspective that is practically impossible, or impractical, or extremely dangerous for people to attain. Drones, for example, can provide a swift bird's-eye view of a disaster scene, which is critical information for rescue operations planning. Another example is the employment of underwater robots to map wreckage or search for human remains after floods, tsunamis, or typhoons have destroyed and obstructed ports and waterways. Because of the miniaturization of sensing technology, search and rescue robots can now carry a growing number of sophisticated sensors, high-definition video cameras, thermal cameras, 2D and 3D laser range finders, sensors for measuring chemical, biological, and radiological contamination, and so on, allowing for more precise and quick cartography. Because these robotic assets are not affected by cloud cover, they are becoming an excellent complement to space-based remote sensing, which is still necessary to cover broad areas. The addition of these advanced sensors to unmanned search and rescue robots allows these unmanned assets to perform damage assessment missions while keeping human operators safe. Unmanned systems can now create realistic three-dimensional (3D) maps of the environment, indicating objects of interest, human survivors, as well as possible risks such as fires or chemical spills, in these 3D models. In the assessment phase, when human search and rescue teams must pick which buildings' structures to explore first, such maps are quite useful. These 3D maps can also be used for post-crisis debris mapping, which can aid in the coordination of recovery efforts and the structured removal of debris. Remote experts, perhaps on the other side of the world, may now examine damage to structures using live, high-quality data collected by unmanned devices, thanks to advances in telecommunication technology. The structural integrity of buildings or shipwrecks can benefit greatly from such remote expert study. During a crisis, unmanned assets equipped with advanced sensors play an essential role as data gatherers, not just to support urgent rescue activities. Indeed, in the aftermath of a disaster, a legal battle frequently ensues between victims, authorities, and insurance companies. Unmanned devices collected accurate, time-stamped, and geo-referenced data during the crisis, which might be used as evidence to settle these issues. Second advantage of using SAR robot is faster. In a search and rescue situation, time is crucial because the chances of individuals surviving drop rapidly. As a result, it is critical to deploy all search and rescue equipment as soon as feasible. Traditional search and rescue assets, rescue helicopters, rescue boats, etc., are frequently overcrowded during a significant crisis, for example, when evacuating casualties. The rapid deployment of readily available unmanned rescue gear can significantly speed up rescue efforts. One of the key advantages of largely airborne unmanned equipment is that they allow human rescue workers to get a worldwide picture of the situation and threats in the crisis region very rapidly. As a result, search and rescue personnel may organize their activities more quickly, rather than needing to wait for satellite imaging or a ground-based assessment. Third advantage is safer. The unmanned systems keep human rescue personnel out of harm's way, which is an evident advantage of robotic systems over their manned equivalents. This is especially critical in earthquake response scenarios, as search and rescue crews must now enter partially demolished structurally fragile buildings to look for survivors, fearful of aftershocks bringing the entire structure down. Indoor drones and ground robots are specifically suited for these activities. As seen by the catastrophic events in Fukushima, when a tsunami caused the meltdown of 3 nuclear reactor cores, exposing the environment to nuclear radiation, chemical, biological, or radiological crises pose a tremendous issue for human relief workers. In such situations, robotic assets may be the only way to properly address the problem without endangering additional human lives. At sea, rescue activities must now be discontinued at night or when the sea becomes too rough, as it would be too risky for human search and rescue personnel. Although robotic assets have difficulty in harsh environmental circumstances such as nighttime operations, strong winds, rain, or a severe sea state, it would be rational to deploy these unmanned systems instead of manned assets for risky activities in a risk assessment framework. Furthermore, because it is easier to detect humans in the water at night than during the day, due to the larger thermal gradient between the human and the water, and because the number of operations at night is limited, unmanned rescue tools show great promise for victim search operations at sea at night.